So we derive this recurrence relation. Okay? But in order to run this example, we need to start somewhere. So we should have some starting point. Okay? Yeah. So here, initial conditions. The function, this recurrence relation, should have some base cases, initial conditions. So that's the boundary cases. So what are the boundary cases? When the first variable equals 0 or second variable equals 0. That's the boundary cases. All right. When I equals 0, what's the meaning of that? I equals 0. You don't have any item there for your pick. Okay? Then in your knapsack, you have nothing to pick. That's why the only answer is 0. You have nothing to put in your knapsack. Okay? Second, j equals 0. The capacity of your knapsack is 0. Although you have many items, but you cannot put anything into your knapsack. Okay? So we have these simple boundary cases to get started. All right. Example. Yeah. So let me use a simple example. First, one simple example. Knapsack capacity 19. Okay? Yeah. So item A, B, C, D. The value 4, 5, 10, 11, 13. Okay? First, let's try to find the answer by observation. Okay? Observation, the size 19. Can we pick? We can easily pick. Okay? 19 equals size number 3 plus 7 plus 9. The corresponding values 4 plus 10 plus 13, 27. Okay? But the question is, yeah, so we feel this is a pretty good solution. But the question, how do you know this is the best solution? Can you convince people this is the best solution? Right? Yeah. All right. So let us use our recurrence relation, dynamic programming, to run this example another time. If we still get the same answer, then we can say that's the best solution. Because based on our analysis, that should be the best solution. All right. So let's work on that. Here, we use that dictionary method. We need to draw that dictionary. Okay. So look up things inside it. Look up the intermediate calculated values in our dictionary. Okay. How to do it? Yeah, because a lot of work. So let me just go a little fast. Our goal, we need to find the value of this two variable function, f of 5, 19. Okay. Number of items, 5 items, the capacity, the size of the knapsack, 19. Okay, find this value. So let's draw this table. Okay. The top row, the capacity numbers. This column, the item numbers. Okay, yeah. All right. So let's work row by row. The first row, trivial, so let me just put the numbers there, because the first row means we can only use item 1. We cannot use other items. Okay, we start from I equals 1. We cannot use other numbers. Then the only way we can do, put that W1 there. That's 4. So you will get a 4 everywhere. All right. Then I equals 2. We can use W1, W2. Then sum of W1, W2, size 7. That means if the size greater or equal to 7, we just put the 2 items there, the value 9. Okay, so we put all there. Yeah. Then for the small numbers, if the knapsack size is 3, you can only put item 1, so the value is 4. Otherwise, 4, 5, 6, you can only put the second item. So value 5. Okay. All right, the first 2 rows, very easy. Row number 3. All right, we add up all the 3 sizes. What's that? 14. So the size 14 or higher, we just put all 3 items, the value 19. That's the easy part. For the smaller end, all right. Before we use the third item, then we just copy from the second row. Okay, so we get that. All right. Now we need to use the third item. Okay, yeah. All right, to work on that, yeah, because I need to use the recurrence relation. To work on that. So here I use some auxiliary data to help me. Auxiliary data, what's that? That corresponds to this part. Okay? The capacity size J minus Wi. What is Wi? Currently, row number 3, the Wi is 7. Okay? So each number minus 7, I put there. Okay? Because I need to use I minus row, that is the second row, I minus row, second row, and the value, I need to compare these 2 values. One is the same J, under the same J, okay, that number. Another is the same row, but under I minus this auxiliary row number. Okay, yeah, so that's how we need to. So here you can see this is the way we organize our data. Okay, yeah. Sometimes it may not be very easy, but we need to organize in this way. All right. The good thing, so we just focus on the second row. Okay, we focus on second row. We only use data in the second row, but we need to compare these 2 locations. Oh, plus VI. VI here is 10. Okay, VI we use 10. All right. 7, 0. Because under 0, nothing. That means 0. So 0 plus 10. 10 is greater than 9, right? So we should put a 10 here. Okay. Yeah. Yeah. So why all 3 10? Yeah, because for all these 3, the F number all 0, right? Because before that, that's 0. So 10 plus 0 beat all these 3 numbers. So we use the larger one, 3 10s. Okay, all right, yeah. Next one. All right, this time still 10 plus the number corresponds 3, so 14. 14 higher than this one, so we use 14. Okay, yeah. All right. Next one, 4, 10 plus the number under 4, second row, right? Yeah, this arrow, second row, this one. 10 plus 5, 15. 15 greater than 9, so we put 15 here. All right. The next one, 5, 10 plus the number, second row, under 5, still 15, better than 9, so we put 15 here. Okay. The next one, 6, second row, under 6, 5 plus 10, still 15, better than 9, so we put 15 there. Okay. All right. So we finish here, we finish row number 3. Yeah. Hope you can follow it. Okay? Hope you can follow it. That's why I work on, this relatively complicated example. Let me work on row number 4. When we work on row number 4, we need to use data from row number 3. Okay? Only data from row number 3. Yeah. All right. This time, we need to update our auxiliary numbers. Yeah. Because item 4, before we get the size of 8, we just use the best solution from the previous row. Okay, here we just copy. Yeah. All right. Then the upper side, because the capacity of these 4 items adding together, 22 more than 19. So we don't have that part. So we don't worry about that. All right. All right. So now let's work on one by one. Now, remember, auxiliary number. Each j number minus the weight size 8. So 0, 1, all the way through the end. Yeah. And vi, this 11. Okay. So we use 11 plus the number of the third row under 0. That's 0, so 11. Okay. Yeah. 11 better than 10. We put 11. 11. Yeah. Still. Yeah, because this could give us a 0 number. 11 plus 0, still 11, better than 10, we put that. All right. For this one too, also give us 0, 11 plus 0, 11, but not better than 14. 14 is better, so we use 14 here. Okay, yeah, here's 14. All right. Next one, this one, 3. 3, under 3, we have 4. 4 plus 11, 15. 15, same as that. So it's okay. So we use 15. Okay, yeah. 12, 4, row 3, we get a 5. 5 plus 11, 16. 16 better than 15, so we use 16. On the 5, still 5, 16, better than 15, so we use 16. Yeah. Under 6, row 3, 6, still 5, 16, but 19 is better. So we take 19. Yeah, because one of the larger numbers here, so we pick the larger one. Okay, 19. All right. Next, size 15, 7, under 7, row 3, that's 10. 10 plus 11, 21, better than 19, so we use 21. Okay, all right. Next one, size 8, under 8, still 10. 10 plus 11, 21. 21 better than 19, so we put 21. That one, 9, under 9, still 10, 21. Yeah, 21 better than 19, we use 21. Okay, all right. 10, under 10, right, size 10. 14, this time 14. 14 plus 11, 25. Right? Yep. 25 better than 19, so we use 25. Okay? All right. 11, 15, 11, 26 better than 19, so we use 26. Okay? So we get row number 4. All right. The last one, the final row number 5. We need to use row number 4. Okay? But the size 9, before 9, we copy from the previous row. Yeah, before 9, yeah. Then next, VI, we need auxiliary numbers. Yeah, that's auxiliary numbers. Okay, all right. 13 plus 0 better than 11, 13. 13 plus this size, also 0, worse than 14, we use 14. Okay, 13 plus 2 worse than, not 2, the function number under 2, that's 0, worse than 15, we use 15. All right. 13, the number under 3, previous row 4, 4 plus 13, 17, better than 16. we use 17. Okay, all right. 4, under 4, previous row, 5 plus 13, 18, better than 16, we use 18. Okay, all right. Then 5, under 5, still 5, 18, worse than 19, we use 19. Okay, all right. 6, under 6, still 5, worse than 21, we use 21. Okay, 7, under 7, 10. 10 plus 13, 23, better than 21, so we use 23. Right? Under 8, previous row, 11, 24, better than 21, we use 24. 9, also 11, 24, worse than 25, we use 25. Okay, all right. 10, under 10, 14 plus 13, 27, better than 26, so we use 27. That gave us this 27, the final answer. All right, that final answer is the best solution. Okay, now we can say nobody can beat this 27. It is optimal. Okay, and we use these 3 items to get 27. Okay, so we complete the solution. Yeah. All right, but at the end, I want to, just extend a little bit. Yeah, hope it's not too long. Rewrite the knapsack problem. Okay. Original version like this, the constraint like this, right? Yeah. But here, each item we use coefficient A1, A2, AI, but that coefficient can only be 0 or 1. Yeah. Because each item you can only select or not select it. Only 2 choices. So 0 and a 1. Yeah. All right. That's the original knapsack problem. Right? Yeah. We need to determine these coefficients such that this number is the maximum. That's the original question. All right. Next, I want to modify this version a little bit. The modification I only put here. I allow each item selected more than once. So that's why I make AI greater or equal to 0. You can do 2, 3, 4, 5, if you have that condition satisfied. Okay? So I change the original meaning a little bit. The question is how to find the maximum of this function. So this is the modified version. Okay? Yeah. All right. So based on our subproblem, yeah, because we can get a recurrence relation quickly. Yeah. For this case, how do we get a recurrence relation? First, we need to define our subproblem. The subproblem here is very simple. We only use one parameter, the capacity J. F of J means the highest value in the knapsack for the selected items. Okay, that's the definition. You can use all the items, no restriction. Okay, but you need to get the highest value. Okay, that's the F of J. Now, here you can see the recurrence relation. We using each weight many number of times. Now we can do single piece reduction. Okay, if we take away one item, okay, that means we take away the size by Wi. Okay, so then your size will become J minus Wi. Okay, then you get the maximum value for that size, but you add a Vi back. Okay, you get this expression. But you consider all possible I. In that case, we can get a recurrence relation like that. The maximum value for all the possibilities of that. That's the recurrence relation after this modification. See? Yeah. So, All right, so I do not want to, use too much time. So let us stop here. That's all 5 parts for this dynamic programming. All right, so let's stop here. Yeah.